Welcome back to the deep dive. We have a really fascinating topic lined up for you today.
We really do.
Usually when we sit down at these microphones, we're parsing through a stack of dense academic journals,
Right.
or maybe a 50-page white paper on global economics.
Yeah.
We're used to dealing with high-level, very polished, professional analysis.
That is the standard operating procedure, yeah.
Yeah,
We take the complex and try to make it accessible for you.
exactly. But today
Took-
we're doing something completely different. We are going back to basics.
Correct.
We're going back to school, literally.
We are. But it's not just a nostalgia trip for you. It's much more than that.
No, not at all. So here's the setup. We have in front of us a chapter from a science textbook.
Right.
The document is titled The Shepherd's Stone, A Guide to Magnetic Science. Specifically, we are looking at Chapter 14.
Chapter 14, yeah.
Now, if you just look at the raw text, it's pretty standard fare. It looks like a curriculum designed for maybe a Class 6 or Class 7 student.
Mm-hmm.
It covers the absolute fundamentals of magnetism.
We're talking about poles, magnetic fields, attraction, repulsion, basically the building blocks of physics.
Right. It's the kind of stuff everyone learns when they are 12, and then most of us promptly forget the details.
Until we're trying to figure out why our GPS is acting weird.
Exactly. And here's the twist, and frankly, the reason we are recording this deep dive today. We aren't just reading the chapter.
No.
We are reading a specific PDF of this chapter that belongs to a student named Aram.
Aram is, a very active reader. Let's put it that way.
Active is polite. Aram has absolutely destroyed the margins of this PDF
Completely cover them.
with digital sticky notes, highlighted text, and what I can only describe as a running commentary of skepticism, humor, and surprisingly deep scientific insight.
It's really a unique document.
Yeah.
On one layer, you have the textbook, which is trying to be very authoritative, very structured, very, classroom science.
Right.
And then on top of that, you have this layer of real-time reaction from a student who is clearly living on the internet.
Watching YouTube explainers.
Exactly. And isn't afraid to call the textbook out when it feels fake.
It's like watching a mystery science theater version of a physics class.
It really is.
Aram is dropping slang, referencing YouTubers like Mapmen and Physics Girl, and actually fact-checking the curriculum in real time. Oh, and I should mention, a quick ground rule for today's deep dive. Aram is typing fast.
Very fast.
So there are a lot of typos and grammar mistakes in these margins, but we are going to completely ignore the typos and grammar mistakes.
Absolutely.
We are focusing purely on the ideas. The spelling doesn't matter. It's the internet generation.
Right. The substance is what counts here. And that's what makes this deep dive so interesting. We aren't just going to learn about magnets today.
No.
We are going to look at how a modern student consumes information. We're going to see the friction between the simplified school version of science and the messy, complex, real-world version that Aram is pulling in from the internet.
So our mission is twofold for you today. First, we are going to do a refresher on magnetism. Because honestly, it is one of the most magical and essential forces in our lives, and we take it for granted.
We really do.
We need to understand the physics. But second, we're going to let Aram be our guide.
I love that.
We're going to stop every time Aram stops. We're going to unpack the slang, the skepticism, and the specific YouTube references to see what they add to the lesson.
And I have to say, having reviewed these notes, Aram is often right.
Yeah.
The textbook tends to simplify things to the point of being slightly misleading, and Aram is there in the margins essentially saying, well, actually, it's more complicated than that.
Exactly. We've got ancient Greek shepherds, we've got airport runways, we've got MRI machines turning oxygen tanks into missiles.
It's a wild ride.
It is. So let's unpack this. Let's start where the text starts, the origin story.
The hook?
The hook. The text introduces us to the discovery of magnets. It sets the scene in ancient Greece.
This is the classic folklore. If you open almost any intro to physics book, you'll find this exact story.
The legend features a shepherd named Magnus.
Magnus.
Right. So picture this. It's ancient Greece, picturesque mountains. Magnus is out there grazing his sheep and goats.
Just a normal day.
He's hiking around, minding his own business. He's carrying a wooden stick to herd the animals. But, and this is the crucial plot point, the stick has an iron tip or casing at the bottom to protect the wood.
That iron is the key variable.
So Magnus is walking along, and suddenly the iron tip of his stick hits a large black stone on the ground.
And it sticks.
It just sticks. The text says he has to use much effort to pull it free. He's confused. He realizes the rock is actually grabbing the iron.
And Historically, this rock is what we call magnetite or lodestone.
Okay.
The chemical composition is F3O4. The text tells us that the rock was named magnetite after the shepherd Magnus.
Right.
And that is where we get the word magnet.
It is a very neat, very tidy little story. It wraps everything up in a bow. Shepherd named Magnus finds the rock. Rock is named magnetite. Boom. History solved.
Perfectly packaged for a 12-year-old.
But Aram is not buying it.
Not even for a second.
There is a digital note scribbled right next to this paragraph. Aram writes, quote, "Side note, it's giving cap, but I mean, it's a story, so I mean, it's fine."
It's giving cap.
I love this phrasing so much. For anyone listening who isn't fluent in Gen Z slang, cap basically means a lie, an exaggeration, or nonsense.
Right.
To cap is to lie. So Aram is looking at this textbook origin story and immediately flagging it as fabrication.
And honestly, Aram is demonstrating excellent historical intuition here.
Really?
Oh yeah. This story of Magnus the Shepherd is almost certainly a myth. It appears in the writings of Pliny the Elder, but he was writing centuries after the fact.
Yeah, I see.
It's an etiological myth, basically a story invented retroactively to explain where a word comes from.
It's like the story of Newton and the apple falling on his head. Did it happen exactly like that? Probably not. But it's a really useful narrative device.
Precisely. In reality, the magnetic properties of lodestone were likely discovered independently by many different cultures over a long period.
That makes sense.
The Greeks knew about it, but so did the Chinese, the Indians. The Chinese were using lodestone for geomancy, basically feng shui and early compasses, long before the story of Magnus was standardized in Western textbooks.
What I love about Aram's note is the concession at the end. It's giving cap, but I mean, it's a story, so I mean, it's fine.
That is a very mature approach to reading a textbook. Aram is basically saying, I know you are lying to me to make this interesting, and I will accept it as a fable, but don't think I actually believe it's historical fact.
It sets the tone for the entire document. Aram is willing to play along, but only if the science holds up.
And the science does pick up immediately after the story. The text pivots from the shepherd on the mountain to the modern world.
Right. It lists the applications. Telephones, televisions, washing machines, generators. It says the discovery revolutionized science and technology.
And that part is definitely not cap.
No, that is the understatement of the century.
Yeah.
If you remove magnetism from the equation of modern life, everything just stops. The lights go out because the turbines stop turning.
The internet dies because the hard drives stop spinning. We are instantly back to the Stone Age.
So let's move into section 1 and actually define the object itself. We throw the word magnet around constantly, but what is the technical definition the text provides?
The text gives us a working definition. A magnet is an object that attracts substances made of specific materials, namely iron, nickel, and cobalt.
Iron, nickel, cobalt. The big three.
Those are the ferromagnetic materials.
I want to pause on this because the text moves on really quickly, but I feel like this is a point of confusion for a lot of people. I think the average person assumes metal equals magnetic.
Oh, absolutely.
Like, if I have a piece of metal, a magnet should stick to it, right?
That is a massive misconception. Aram doesn't comment on this specifically, but the text is very clear. Iron, nickel, and cobalt. If you take a magnet to a piece of copper, nothing happens.
Okay.
If you take it to aluminum, nothing happens. If you take it to gold or silver, nothing happens.
Why is that? Why only those three?
It comes down to the electrons. Without getting too deep into quantum mechanics here, magnetism arises from the spin of electrons.
Okay, stay with me.
In most atoms, electrons spin in pairs, one up, one down. Their magnetic fields cancel each other out. It's a wash.
So they neutralize.
Right. But in iron, nickel, and cobalt, you have shells of electrons that are unpaired. They're spinning in the same direction.
Ah.
And crucially, these atoms like to line up with their neighbors in groups called domains. So you get billions of atoms all shouting in the same direction, magnetically speaking. That's ferromagnetism.
So when the text introduces the carpenter's dilemma, that's what we're seeing in action.
Right, the scenario where a carpenter accidentally mixes iron nails with wood shavings. How do you separate them?
You don't use tweezers. You use a magnet. The magnet pulls the iron nails because they have those unpaired electrons waiting to align, and it leaves the wood behind.
It's a simple experiment, but it neatly categorizes the material world into two buckets for the student: magnetic and non-magnetic.
The text also introduces the concept of the magnetic field. It describes it as the region around the magnet where this force can be felt, represented by lines of force.
This is a really important abstraction. A magnet isn't just a rock. It's an object surrounded by an invisible 3D structure. The lines of force are just a way for us to visualize that map.
So we know what it is. Now we need the rules of engagement. Section 2 outlines the properties of magnets. There are 4 main ones listed here. Let's run through them.
Sure. Property number 1 is the attractive property. Magnets attract magnetic substances, but the text makes a specific distinction. The attraction is strongest at the ends.
The poles.
Right. Property number 2, poles of a magnet. Every magnet has 2 poles, north and south. The magnetic force is maximum there.
So it's not evenly distributed?
Exactly. If you dip a bar magnet into a bowl of iron filings, they don't coat the whole bar evenly, like breadcrumbs on a fish stick.
Right.
They cluster at the tips. You get these big fuzzy beards of iron at the ends, and the middle is almost bare.
Which physically proves the field is concentrated at those points.
Exactly. Property number 3 is the directive property. This is the one that changed human history.
Huge.
A freely suspended magnet, like one hanging from a string, will always align itself in the north-south direction.
Which is the entire basis of the compass.
And think about how weird that is if you don't know the science.
Yeah.
Imagine if every time you dropped a pencil, it pointed toward Paris.
That would be terrifying.
It would imply there was some invisible force in Paris grabbing the pencil. The directive property proves that the magnet is interacting with a much larger magnetic field, the Earth's.
And finally, property number 4 is the magnetic axis, which is just the imaginary line joining the poles. But then the text introduces a concept that I find really fascinating, the indivisibility of poles.
Right, the text proposes a thought experiment, breaking a magnet.
Okay, so if I have a stick that is painted red on the left and blue on the right, and I snap it in the middle, I have a red stick and a blue stick. Separation achieved.
But magnets don't play by those rules. The text says if you break a magnet into 2 pieces, you don't get a north piece and a south piece. You get 2 smaller magnets.
Just automatically.
Automatically. Each one is a completely new north pole and south pole.
And the text says, no matter how small you break it, both poles will always exist. You cannot separate them.
This is a fundamental law of nature. In physics, we say there are no magnetic monopoles.
Monopoles, meaning one pole.
Right. You can have a single electric charge. An electron is just negative. It doesn't need a proton attached to it. But you cannot have a north pole without a south pole. They are 2 sides of the same coin.
So even if I smash it down to a single atom of iron?
That atom is a dipole. It has a north side and south side's dipoles all the way down.
That is wild. Okay, so we have the poles, and we have the golden rule of interaction. Like, poles repel, unlike poles attract.
North pushes north away. North pulls south closer. Simple.
Or is it?
There we go.
This brings us to section 3 of our deep dive, and this is where Aram absolutely takes over the show.
Yes.
The text discusses the test for magnetism.
So the textbook offers a standard procedure. It says, to check if a metal bar is a magnet or just a piece of iron, bring it near iron filings.
Yeah.
If it attracts them, or if it attracts to another magnet, it's a magnet.
It seems like common sense. If it sticks, it fits. But Aram has circled this paragraph with a bright digital pen and written a massive note. It starts with 2 words in all caps. Ding dong.
Ding dong. I assume this is the sound of the incorrect buzzer on a game show.
That is my interpretation, too. Aram writes, quote, ding dong attraction is not a sure test for magnetism, as materials like iron can get attracted to magnets without being a magnet itself.
Aram is 100% correct. This is a trap that students and adults fall into all the time.
Let's break this down. If I hold a magnet near a paperclip, the paperclip sticks.
Correct.
But the paperclip wasn't a magnet before I picked it up. It was just a piece of wire.
Exactly. This is the phenomenon of induction. When you bring a permanent magnet near a piece of ferromagnetic material like soft iron, the magnet's field temporarily forces the iron's domains to align.
So it turns the iron into a magnet.
Yes, for as long as they are close to each other.
So the attraction I'm seeing isn't between 2 permanent magnets. It's between a magnet and a piece of iron that is just mirroring it.
Right. So if you see 2 things attracting, you don't actually know the truth. Is it 2 magnets? Or is it 1 magnet and 1 piece of gullible iron? You can't tell just by looking at them stick.
So standard physics textbooks usually say that repulsion is the sure test. Because a piece of ordinary iron will never repel. It will always try to align and stick.
Right.
So if something pushes back, it must be another magnet.
That is the standard Class 6 answer. Repulsion is the proof.
But wait, Aram isn't done. This is the best part. Aram adds another layer of complexity that, frankly, I didn't expect to see in the margins of a grade school text.
What does the rest of the note say?
The note continues, and also, repulsion is also not a sure test of magnetism, as diamagnetic materials repel magnet no matter what, and it is not a magnet.
Wow. Okay, I am genuinely impressed. Aram is bringing up diamagnetism.
What is that? I've heard the word, but break it down for us.
So usually we just talk about ferromagnetism, the strong attraction we see in iron. But actually, all matter interacts with magnetic fields in some way.
Really? All matter.
Yes. Diamagnetism is a property found in things like water, wood, carbon, even gold. When you apply a magnetic field to them, they create a weak internal magnetic field in the opposite direction.
In opposition, so they push away.
Yes. They are repelled by magnets. Now, usually this force is incredibly weak. You can't feel it with your hand. But if you have a strong enough magnet and a sensitive enough setup, you can clearly see it.
Is this related to the levitating frog?
Yes. That is the famous experiment. Scientists used a massive 16 Tesla magnet to levitate a live frog. The water in the frog's body was diamagnetic. It repelled the magnet so strongly that it overcame gravity.
And the frog just floated.
The frog floated, unharmed, by the way.
So Arm is arguing, if I see something being repelled, it might be another magnet, or it might just be a chunk of diamagnetic material, like bismuth or pyrolytic graphite.
Technically, yes. Aram is being incredibly pedantic here, but in the best possible way.
I love it.
Aram is highlighting that magnetic interaction is a spectrum. It's not just a binary stick or don't stick.
Ding dong indeed. Aram is not letting this textbook get away with any oversimplification.
It creates a great mental image of this student sitting there, maybe having just watched a YouTube video about levitating frogs, and thinking, wait a minute, this book is lying to me about repulsion being the sure task.
It's critical thinking in action. I love it. Now, speaking of making things magnetic, the text moves on to manufacturing magnetism. Section 4, how do we make these things?
The text outlines 2 DIY methods, the single touch method and the double touch method.
The single touch sounds like a magic spell. You place an iron bar on the table, you take a bar magnet, you rub it along the iron bar from one end to the other, you lift it up, bring it back to the start, and do it again.
The key instruction here is, without changing direction, you have to go in a loop.
Why? Why can't I just scrub it back and forth like I'm cleaning a stain?
Because remember those domains,
Yeah.
those little atomic groups we talked about, you are trying to comb them. You want them all to point north.
Okay.
If you stroke one way, you align them. If you stroke back the other way, you mess them up again. You're just undoing your own work.
It's like petting a cat backwards. Don't do it.
Exactly. And the double touch method is similar, but you use 2 magnets starting from the center and pulling outwards. It's more efficient because you're aligning both halves of the bar simultaneously.
The text also mentions electromagnets, which use electric current, which is a huge topic on its own, but Aram has added a note here about a method the text misses entirely.
Yes, Aram writes, but there is another, pun intended, method in which heat up a metal and cool it all in a magnetic field. This is what companies usually use.
Okay, first of all, let's address the elephant in the room. Another, pun intended. Aram, what is the pun?
I have no idea.
Is it on heat? Is another supposed to sound like an otter?
I've been trying to figure this out since I read it. Maybe it's a pun on cool. Or maybe Aram thinks another sounds like anode. Honestly, I think the pun might just be lost to history.
It's a complete mystery.
But the science is not a mystery. Heating and cooling.
Yeah, let's talk about that.
This is referencing a very advanced concept called the Curie point. Pierre Curie discovered that if you heat a ferromagnetic material like iron above a certain temperature, about 770 degrees Celsius, it stops being magnetic.
It just loses the magic entirely.
The heat gives the atoms so much thermal energy that they vibrate violently. They shake themselves out of alignment. The domains basically shatter.
So heat kills the magnet.
Yes, initially. And this is Aram's point. If you keep that metal hot, place it inside a really strong external magnetic field, and then let it cool down slowly.
Oh, I see. As it cools, the atoms slow down, and because there is a field there forcing them, they lock into place aligned with it.
Exactly. It freezes the magnetism into place, and because they cooled into that formation, they are much harder to disrupt later. This creates permanent magnets. This is how they make the really strong magnets in your headphones or your electric car motor.
So once again, Aram is bringing the industrial context to the classroom, saying, rubbing it with a stick is cute, but here's how the factories actually do it.
It shows a real curiosity about how things are actually made, not just the classroom experiment version.
Now let's zoom out, way out. We've looked at the atomic level. Now let's look at the planetary level. Section 5, the Earth as a giant magnet.
This is fundamental. The text explains that the reason a compass works is that the Earth itself acts like a huge bar magnet.
It says this is due to the movement of molten iron in the Earth's core.
Correct. The geodynamo. We have a solid inner core and a liquid outer core. That liquid iron is constantly churning due to convection and the Earth's rotation. Moving metal means moving electrons. Moving electrons create a magnetic field.
The text makes a specific point about orientation that always trips people up. It says the Earth's magnetic south pole lies near the geographic north pole.
This is the classic compass confusion. Think about it. The needle of your compass is marked N for north. That means the tip of that needle is a north pole.
Okay, I'm following.
And we know that unlikes attract. So for the north pole of the needle to be attracted to the Arctic, what must be sitting in the Arctic?
A south pole.
Exactly. Magnetically speaking, the top of the world is the south pole, but because we call it the north on maps, we refer to it as the North Magnetic Pole, just to keep geographers from having a breakdown.
That is so counterintuitive.
But strictly speaking, the physics is reversed.
Okay, here is where we get my absolute favorite Arum note of the entire document. This is a deep dive within a deep dive.
The map-men connection.
Yes. Arum writes, quote, FUN fact, the ICDICs for the MEPN and CGP gray for telling me that the magnetic poles move everywhere and airport runways are named because of the magnet poles, so some airports need to change their runway numbers every some number of years.
There is so much packed into this note. I just love it.
First, shout out to the YouTubers MapMen and CGP Gray. Clearly, this is where Arum is getting this extra curriculum.
And they are fantastic educational sources.
Oh.
Arum is highlighting a phenomenon called magnetic drift. The Earth's magnetic field is not static. It's not a solid rock buried in the ground.
Right.
It's sloshing liquid. So the poles wander.
They actually move.
Oh, they move a lot. The North Magnetic Pole has been racing from the Canadian Arctic towards Siberia at about 50 kilometers a year recently.
And the real-world consequence Arum identifies is airport runways. I had no idea about this until I read this note. Explain how that works for us.
It's a massive logistical headache. Pilots navigate by magnetic compass heading. So runways are named based on their magnetic heading, rounded to the nearest 10 degrees.
Give me an example.
If a runway faces due east, that's 90 degrees on the compass. So they paint the number 09 on the runway. If it faces south, that's 180 degrees. They paint 18.
So when the pilot is coming in to land, they look at their compass, they see 180, they look out the window, they see a big 18 on the ground, and they know they are perfectly lined up.
Exactly. But because the magnetic pole is moving towards Siberia, the magnetic heading of that concrete strip changes over time.
Oh, wow.
Eventually, 180 degrees becomes 176 degrees, then 174. Eventually, it's closer to 170 than 180.
And then what happens?
The airport has to literally shut down the runway, send out a crew, scrape the paint off the tarmac, and rename the runway 17.
That is wild. We literally have to update our concrete infrastructure because the planet's liquid core is shifting.
It happens all the time. Airports in Florida, London, Canada, they've all had to renumber runways. Arum calls it a fun fact, but for the airport managers, it's probably a very expensive fact.
But I love that Arum connects the abstract Earth as a magnet to the tangible paint on a runway. It's brilliant connection making.
It anchors the science in reality for the reader.
But magnets aren't just for creating runways. They can also be destroyed. Section 6 covers magnet mortality.
Demagnetization. The text lists 3 ways to kill a magnet: dropping it, hammering it, or heating it.
Violence and heat.
Essentially, yes. It all goes back to those domains we talked about. If you hit a magnet really hard with a hammer, you send a mechanical shock wave through the material.
Right.
It jars the atoms. Some of them get knocked out of alignment. If you do it enough times, the order turns into chaos, and the magnetism just fades away.
The text also gives advice on life support, how to store them so they don't die.
It says to keep them in pairs, opposite poles on the same side, and use soft iron keepers across the ends.
What exactly is a keeper?
A magnet is always trying to close its magnetic loop. The field lines come out of the North Pole and desperately want to get to the South Pole. Air is a really difficult path for magnetism. It has high resistance or reluctance. If a magnet has to push its field through air for years, it essentially gets tired. It can self-demagnetize to lower its energy state.
So the keeper acts like a bridge.
Exactly. It's a piece of soft iron that connects the north to the south. It gives the field lines a super easy highway to travel through. It closes the circuit and preserves the magnet strength indefinitely.
It's like putting the cap back on a marker so it doesn't dry out.
That's a great analogy. Ideally, yes.
Now we move to the caution section, and this brings us to another round of Arum's Internet Academy. The text warns, Magnets should not be kept near CDs, credit cards, computers, or medical devices like pacemakers.
Standard safety advice. Strong magnetic fields can erase magnetic storage media.
Aram has a lot to add here. The note says, quote, "The physics girl has demonstrated that even a small magnet can tamper with the security/verification strip in credit cards, so be careful."
Again, citing a source. Physics Girl is Diana Cowan, a wonderful science communicator on YouTube. Aram is noting that it doesn't take a giant junkyard magnet to ruin your day.
How does that actually work? The credit card strip, I mean.
The black strip on the back of your card is basically magnetic tape, like an old cassette.
Yeah.
The date of your account number is written on it by magnetizing tiny sections in different directions. North, south, south, north.
That's a code.
It's binary code written in magnetism.
And if you run a magnet over it,
You scramble it. You force all those tiny sections to point the exact same way. The data is gone. It's like smearing ink on a page. The card reader just sees noise.
then Aram pivots to computers. Quote, "Magnets must not be kept with computers or PCs, as sometimes the fans can get stuck and other weird things happen."
Weird things happen, a very broad scientific category.
Ignoring the typos, as promised.
Right. But the fan point is really specific and correct. Computer fans use brushless DC motors. They rely on permanent magnets and sensors to spin. If you stick a strong magnet to your PC case right next to the fan, you can physically break the motor or completely confuse the sensors.
And no fan means overheating. Overheating means a dead computer.
Exactly.
And then we get a blast from the past. Aram mentions, quote, "CRT TVs like the oldie ones interfered heavily with magnetic field."
Oh, the nostalgia. I can hear the high-pitched whine of the CRT just thinking about it.
Aram is a bit shaky on the source here, writing, quote, "I think I'm not so sure Neil Green, not red or blue, did this experiment, or it was Linus Tech Tips or LLT."
I love Neil Green, not red or blue. And I have to assume this is a mashup of Neil deGrasse Tyson and Hank Green.
Or maybe neither of it. It sounds like Aram has created a composite super YouTuber in their mind.
But the memory is accurate regardless of who did it. If you brought a magnet near an old tube TV, a CRT, the colors would go absolutely psychedelic.
I definitely did this as a kid. You put the magnet near the glass, and the image would warp and turn purple and green.
You were playing with fire there.
My parents were not thrilled.
So the way a CRT works is by shooting a beam of electrons from the back of the tube to the screen. Electrons are charged particles. When they pass through a magnetic field, they experience a force, the Lorentz force. They get deflected.
So the beam that was supposed to hit the red pixel gets pushed sideways and hits the green pixel instead.
Precisely. You are physically steering the electron beam with your hand magnet. It creates that rainbow distortion. And if you did it too much, you could permanently magnetize the metal shadow mask inside the screen, and the TV would be stuck like that forever.
Aram's note here, "Weird things happen," sums it up pretty well. Magnets and delicate electronics usually don't mix.
Although, interestingly, modern screens, LCDs, OLEDs, aren't affected by magnets in the same way because they don't use electron beams at all. So this is a bit of legacy knowledge that Aram is preserving.
Finally, we get to the modern applications. Section 7. We've gone from the shepherd's stone to the MRI.
The text lists the everyday stuff first. Refrigerator doors, stickers, electric motors, speakers.
Speakers are cool converting sound to electric signals and vice versa. It's all magnets pushing against coils.
And junkyards, using huge electromagnets to lift scrap steel.
But the big one is the MRI, magnetic resonance imaging. The text calls it a machine for body scans.
It is the ultimate application of the principles we've discussed. It uses a magnetic field tens of thousands of times stronger than the Earth's field to align the hydrogen protons in your body.
And Aram has a first-hand report. Aram writes, quote, "I've seen one of these IRL, it's super cool, but do not get anything that can get attracted to magnets near this, as it will launch it with insane speeds."
Launch it with insane speeds. Again, typos aside, the urgency is real.
Aram is not wrong, though, right?
MRI safety is incredibly strict. We call it the missile effect. The electromagnets in an MRI are supercooled with liquid helium. The field is always on, and it is monstrously strong.
So if you walk in with metal,
If you walk into that room with a metal oxygen tank or a wheelchair or even a set of keys, the machine becomes a literal cannon.
the magnet pulls it in.
It doesn't just pull it. The gradient of the field is so steep that the object accelerates almost instantly. It will rip a fire extinguisher out of your hands and slam it into the bore of the machine at 40 miles per hour.
That's terrifying.
There have been tragic accidents involving oxygen tanks. It's no joke.
It really highlights the sheer scale of force we have mastered over centuries. We started with Magnus struggling to pull his stick off a rock on a hill, and now we have built donuts of wire that can suck a chair across a room instantly.
And Arm's warning, do not get anything that can get attracted to magnets near this, is probably the most practical life advice in the entire textbook.
So we've reached the end of the chapter and the end of Aram's notes. What a journey this has been.
It really was.
We started with a piece of folklore that Aram rightly identified as Cap. We learned that magnets attract iron, nickel, and cobalt. We learned that poles are inseparable. You can't have a north without a south.
We learned that attraction is a flimsy test, and thanks to Aram, we know that even repulsion has a diamagnetic loophole involving levitating frogs.
We learned how to make magnets by stroking them, or as the companies do, heating and cooling them at the Curie point. We learned that the Earth is a sloshing magnet that forces airports to repaint their runways because the poles are wandering.
A fact brought to us by Mapmen and Aram's YouTube habits.
And we learned that while magnets are useful for sticking photos to the fridge, they are also capable of destroying credit cards, warping old TVs, and turning metal objects into missiles in an MRI room.
It's a powerful duality, creation and destruction, stability and chaos.
And I think that's what makes Aram's contribution so special. The textbook gives us the what. It gives us the clean, sanitized rules. But Aram gives us the so what.
Aram connects the dots for us. Aram asks, is this story true? Does this test actually work? What happens if I take this into a hospital? That is the essence of scientific thinking. It's not just memorizing definitions, it's interrogating the world.
Exactly. The textbook is the map, but Aram is the explorer, walking the terrain, pointing out the pitfalls and the scenic outlooks.
And using terms like ding-dong and cap along the way, which frankly makes the journey much more enjoyable.
So here is a final thought for you to chew on, inspired by our deep dive today.
What's that?
We talked about the Earth's magnetic poles moving. Aram told us about the runways changing. We know the poles have actually flipped completely many times in Earth's history. North becomes south.
Geomagnetic reversal.
Wow.
It happens every few 100,000 years. And we're technically overdue for one.
Right. And we are living in a society that is more dependent on magnetic technology than ever before. Satellites, power grids, navigation.
All relying on the stability of that invisible field.
So if Aram is right to worry about a credit card strip getting wiped by a fridge magnet, what happens when the Earth's magnet decides to go haywire? We are floating on a giant, unstable dynamo, and we usually take that stability completely for granted.
That is a very unsettling but very relevant question.
Something for you to think about the next time you look at a compass or stick a drawing to your refrigerator.
Indeed.
Thanks for joining us on this deep dive into the shepherd's stone and the brilliant mind of Aram. We'll see you next time.
Goodbye.